Welcome back to the deep dive. I mean, have you ever thought about how a surgical robot actually operates? It's swinging a scalpel around delicate, vital organs, but it moves in this near absolute, terrifyingly precise silence.
Yeah, it's an eerie thought when you really picture it. You
Yeah.
have these massive, incredibly powerful machines moving with, like, the stealth of a shadow.
Right, it feels like magic. But looking through the advanced engineering deck we're exploring today, EP0054 mechanical vocabulary, it's really just an obsession with microscopic physical choices.
Exactly. And, the deck reveals something wild. The massive, heavy machinery shaping our world is, well, entirely at the mercy of submicron decisions.
Which is our mission today, right?
Yeah.
To decode the physics behind this high-level precision transmission, to see how this actually works.
Hmm.
And the deck starts by blowing my mind right out of the gate with this idea of submicron tooth grinding.
Yeah, they're machining gear teeth down to a precision of less than 1 micron.
Which is insane. I mean, that's 1,000th of a millimeter. So forget the old slicing a human hair analogy. We're talking about, like, smoothing out molecular mountains here.
You really are. And to a machine, smoothing out those mountains changes everything. Because by grinding gears down to that submicron level, engineers completely eliminate high-frequency vibration.
Oh, so that's where the silence comes from.
Exactly.
Mm-hmm.
To achieve that terrifying silence in surgical robots, they use this exact grinding technique on a stationary ring. It's called the circular spline.
Okay, got it.
That's the secret to minimizing the engagement noise when the gears finally mesh together.
Okay, but here's where I get a bit confused. They spend, all this time and money grinding a mathematically perfect, ultra-smooth gear, and then they intentionally ruin the shape of it.
Well, I wouldn't say ruin that.
But the source mentions tooth tip relief, where designers actively thin out the tips of the gear teeth. Wait, hold on. If you spend all that effort making a perfect gear, why shave the tips off? Doesn't that just make the teeth weaker?
You would think so, yeah. But it's because in the real world, metal bends. These particular gears aren't just rigid circles. They use something called a flex spline.
Which is basically a flexible metal cup, right?
Exactly. It's a cup that actually bends and warps to drive the gears.
Wait, so the metal cup is constantly bending while it's spinning?
Yes, it is.
Hmm.
And because it flexes under a heavy load, the gear teeth deform.
Oh, I see.
So by intentionally thinning the tips of the teeth beforehand, engineers compensate for that deformation. It reduces sliding friction at the exact entry and exit points where the gears mesh.
So they're designing for how the metal will behave under intense stress, not just how perfectly it draws on a blueprint.
Exactly.
But, okay, so we've ground this metal down and we're intentionally bending its shape. But bending metal repeatedly is just a universal recipe for snapping it. How do these ultra-thin flexing gears not just shatter under the pressure?
That comes down to what engineers call surface integrity. Because these specific gears are often cut using WEDM, that's wire electrical discharge machining, they're basically slicing the metal with high-voltage electrical sparks.
Wow, that sounds intense.
It is. And that intense heat can easily leave behind microscopic thermal cracks. So they use laser scanning to guarantee absolutely zero micro cracks form during manufacturing.
Finding no cracks is great, but they actually take it a step further to actively prevent them later on.
They do, yeah.
After heat treating the metal, they do something called shot peening. And I've got to be honest, it sounds incredibly destructive. You're blasting this perfectly machined gear with tiny, high-speed metal pellets.
Sounds like a terrible idea.
Yeah.
But blasting it causes a very specific plastic deformation on the surface. And what's fascinating here is the mechanics behind it.
Okay, how so?
It introduces what engineers call residual compressive stress.
Let's unpack that. What does residual compressive stress actually do?
Well, imagine a packed bookshelf.
Okay.
If you cram 5 extra books onto the shelf, they press incredibly tightly against each other.
Right, you can barely pull one out.
Exactly. That is residual compressive stress. By blasting the metal with those pellets, you're packing the surface molecules so tightly together that microcracks literally don't have the physical room to pull open when the gear is placed under high tension.
Oh, wow.
Yeah, it vastly improves the gear's fatigue limit for high-torque applications.
Okay, so we've packed the molecular bookshelf to stop cracking. We've got our submicron finish and our pre-thinned teeth.
Right.
But all of this is static design. What happens when you actually turn the machine on and crank up the speed?
Well, that's where we hit dynamic transmission error, or DTE. This is the comprehensive error measured during actual rotation.
So the real-world test.
Exactly. When the machine spins up, you introduce inertia, friction, and changes in the metal's rigidity. DTE measures how far off the physical movement is from the theoretically perfect digital command.
And the stakes here are massive, right? Because if the DTE exceeds the digital controller's compensation bandwidth, meaning the physical stutter is just too big for the software to instantly fix, entire high-speed vision systems lose synchronization.
They completely fail.
Right. So picture that surgical robot we started with. If the physical gear stutters by even a fraction of a millimeter because of dynamic friction, the robotic scalpel completely misses its target.
Yeah, which really reminds you that having the most advanced software in the world means nothing if the physical variables in motion aren't perfectly accounted for.
We are constantly hyping up AI and code, but today we've journeyed through the microscopic physical reality, keeping those systems alive.
Right, from submicron precision grinding and flex-spline deformation to thermal crack prevention and dynamic motion testing.
It completely changes how you view the machines running our
It
lives.
really does.
And it leaves you with something to chew on. If a microscopic, invisible flaw in a physical gear can completely blind an advanced, high-speed digital vision system, how much of our limitless, software-driven future is actually completely bottlenecked by our physical ability to polish a piece of metal?